what does it say here? It says, remember previous lessons too. When would you feel the most force on your bottom? Ooh, that's an exciting thing. Where would you go the fastest? Ooh la la. And in the loop, which has the highest speed? Your head or your feet? All right, so questions to ask ourselves as we're going along, okay? So some decent questions. But I got a roller coaster. I'm gonna define a few points. I'm gonna say that this is point A. I wanna have point B when we get to the bottom of the valley. We'll have point C at the top of the loop, point D at that next hill, and then point E at the very end. And then we'll add on some values. We'll say that if that's point A, there would be a height A. Height A, 20.0 meters. Point B, I'm going to run out of space for my letters. So I'm just going to say it's going to be at 3 meters. You know, here I've got this dotted line here. Implicitly, I'm saying that that's where I've defined to be my zero height. Height C, (13 meters). Height D, and height E, 0 meters. All right, so you got your highs and your lows. One thing you notice about height D, if this is a true roller coaster, like a coaster, not a powered ride, what do you notice about height D as it compares to height A?
It's less.
Gotta be less, because there's going to be energy dissipation, right? So practically speaking, there would have to be less. All right, so it says find the total mechanical energy of this roller coaster. Well, I think we need to have more information. I think the mass of the roller coaster, I'm going to make it a nice round number of 500 kilograms. And you know when you get up to the top of the roller coaster and the chain pulls you up, 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 and then you get to the top of the crest of the hill, and the butterflies are mounting. Velocity A is going to be 0.5. It's not 0, 0 meters per second. You don't quite come to rest. And then it's woo, and your hands go up in the air and everybody screams, right? Anyway, so the total mechanical energy, you would need to know the mass of the roller coaster because you need that for gravitational potential energy and kinetic energy. And you need the speed in order to say that, yes, there's going to be some kinetic energy somewhere, right? And it could be 0 at the top if they like dropped you from the top. But that's not the way real roller coasters work, so we're not going to roll that way. So total mechanical energy at point A is something that I am able to calculate. I've got enough info for that. Reminder, that would be the gravitational potential energy plus the kinetic energy. Now there are other types of energy. Like we could talk about, if this was a higher level course, we could talk about, I don't know, let's call it rotational energy at point A. That would be the energy due to the rotation of the wheels of the roller coaster. We could talk about, because that's not translational kinetic energy, and we would need to know what's called the moment of inertia of each of those wheels. We'd also talk about maybe vibrational energy, because the roller coaster would be rumbling. We could talk about thermal energy. I'll call it lowercase a. Is there other things we could talk about, like how hot the roller coaster is? I mean, I want to just eliminate all these red ones, because we're not going to go down that level of complexity, but the point is total energy is a lot of stuff. There could be a lot of things built into this thing. We're not going to set the roller coaster on fire, but could there be chemical potential energy locked up in the seats of this roller coaster as we set them ablaze? 100% yes. We're not going to add all that stuff. Okay? So just this basic mechanical, gravitational potential energy and translational kinetic energy. By the way, rotational and vibrational are both types of mechanical energy too, right? We're just avoiding them. We don't have the math skill set for that yet, but you will one day. Anyway, mass times acceleration to gravity times height A plus 1/2 mass times velocity A squared. Sub in our values. I won't narrate all of that. I'll just write it. Don't forget to square the speed. And I trust that we can put all this into one line of calculation. Well, previously, I trusted somebody for their answer. So we're going to get second motions and third motions to get a conviction about this one. I think the answer starts with a 9. Does anybody want to confirm? Got a 9. Ali, what do you say? $162.5. All right, I love it. Anybody want to second that motion? All right, motion carries. Good. And then if we're going to round off to 3 significant figures, because it looks like that's what we're dealing with here. We didn't use the 3.0. That would have been 2 significant figures. So 9.82 times 10 to the power of 4 joules. That's a lot of joules. And we could say therefore and have some sort of a statement there to contextualize the answer. But I want to go on to B. What's the total mechanical energy at points B, C, D, and E? Now, I mentioned the idea of energy loss earlier, but if I go back up to this header, it says with no friction or drag. So with that assumption in mind, what's the energy going to be at points B, C, D, and E? Same, yep. So I could say ETA equals ETB, yada, yada, yada. Equals what we said before, 9.82 times 10 to the power of 4 joules. But just a reminder, that's only because there's 0 energy loss. And in the wild, wild world of physics, that's something that happens in physics classroom, but never in the real world do we get 100% efficiency. There's always going to be drag. There's always going to be the vibrating track. There's always going to be a little friction in the axles, all that sort of stuff. So C, find the gravitational potential energy at point C. Well, we're sort of chunking this out. At position C, we have a height of 13.0 meters. So just a reminder of that, because I don't have it on screen right now, but you have it on your page. So when I say EGC, I'm going to say mass times acceleration due to gravity times height c, plug in my values. And again, I'll poll the room. I think the answer starts with a 6. What'd you get, Wes? 63,765. Say it again? 63,765. Nice. That's what I got too. Beautiful. All right, and then if I was going to do this to 3 significant figures, I might say 6.38 times 10 to the power of 1, 2, 3, 4 joules. I think, yeah, of course I could do a context there for a statement. But again, I want to move on. Find the kinetic energy at point C. Now, I don't have the speed at point C, so I can't directly find the kinetic energy at point C. What could I do? Yeah? I love it. Yeah, take the total energy and subtract away the gravitational potential energy. So E total C equals EGC plus EKC. And he says we're going to get EKC all by itself. E total C minus EGC. Sub in our values. Well, we happen to have already calculated those 2 values, so I'm not going to go back and calculate them again. But remember, we could create a formula for ourselves. You know what? Maybe I'll just go down the rabbit hole really quickly. I know that ETC is equal to ETA. So if I was going to make a general equation for this, I could have said mass times acceleration due to gravity times height A plus 1/2 mva squared minus EGC, mass times acceleration due to gravity times height c. And if I was really committed to the cause, I could factor out what from this? Can you guys see? Can I pull the mass out? Yeah, look at that. I could pull a mass out front, and inside the brackets leave behind, I guess it's a trinomial. But you know, while I'm doing this, my math inner child wants to collect the like terms. EGHA minus AGHC plus 1/2 VA squared. And I'm not gonna lie, like there is some part of me that wants to go back and factor the AG off the first two terms and have like a binomial inside of the brackets, but I'm gonna hold myself back because I just, whatever. Anyway, in the end, whether I sub directly into this because I really felt like I needed to, or if I wanted to just jump from that second line into using my values that I've already calculated, EKC, I could have gone either way. E total C was equal to the unrounded value 98,162.5 joules minus the EGC, which we just calculated, 63,765 joules. And I think the answer starts with a 3. Will, did you get an answer that starts with a C? A 3? All right, this is a redemption story, got it. 34,397.5. I'm sorry, I'm just being silly. All right, 3 sig figs, 3.44 times 10 to the power of 4 joules. Great, therefore, done. Then the question is, how fast is the car going at position C? Well, of course we could say, we can calculate EKC equals 1/2 MVC squared, isolate for VC. And I'll just do all the rearranging in one go. 2 times EKC divided by mass square rooted. But then we also know this EKC value here, you see that it could be written right here? And if I was really in love with generalized equations, I could say VC is equal to, I'll write it in small and I'll zoom in real good. I could write it as VC is equal to 2 times mass times AGHA minus AGHC plus 1/2 VA squared, close bracket, all divided by M. And as I look at that, I think, oh, honey, oh, don't forget I got a square root. But those masses are gone. This becomes mass independent. That's kind of nice. And so I could just sit with that generalized equation, or I could go with the root of having already calculated the EKC in a previous question. And I could say, okay, well, that means that VC is equal to 2 times the unrounded value, 34,397.5 joules divided by 500 kilograms, all square rooted. Now, the reason I keep on bringing up these generalized equations, again, I've talked about this before, but this is a heavily scaffolded question where I'm like stepping you through it and holding your hand as we walk through the woods kind of thing, right? You'd like to be able to generate an equation like that and jump straight to part E, right? Because there ain't no party like a part E party. So what does VC equal? Starts with a 1. Sorry, I got carried away. Audrey? No, Audrey, you're just wringing your hands. I'm sorry.
I guess.
Yeah.
11.729.
Say it again.
11.729.
988. Okay. 88?
Yeah.
All right, cool. Meters per second. Of course, that's going to be about, oh man, I really ran out of space here, about 11.7 meters per second. What did I run out of space for? Oh, because I threw in this little piece of information. Did you know that in 1813, Peter Ewart supported the idea of the conservation of energy in his paper on the measure of moving force? In 1847, Hermann von Helmholtz. Don't these people sound like fictional characters almost? Like this alliteration, my goodness, straight out of the comic books. But formally stated the law of conservation of energy. Anyway, like I think that this is nice to see because here we are, like as students, high school students, we're just like taking this as, rote truth. It's been written somewhere. But this timeline is actually fairly recent. Like, I mean, 1847, I know it's not like within our living lifespan, but like to have formally stated these ideas that recently, you're like, holy smokes, like why wasn't this like some ancient person from Egypt or something that figured this out? This is within the past 200 years. That's remarkable to me. Like anything that happens within the past 200 years, I'm like, wow, that was cutting edge. And you think about how far we've come within 200 years, but I think that that's kind of neat. By the way, this is like a schematic diagram of the apparatus that one of these guys used. I can't remember because I didn't do this recently. I did this last year. Anyway, F, on your own, repeat parts C to E for this problem at positions D and E. I don't want to spend my time doing that. But if you feel like you wanted to build your confidence on this one, and you feel like I held your hand through this, check to make sure. See if you can do it yourself. Go through the process. Consider using the piecewise method or using the generalized equation method. Totally up to you. But again, that's just like a confidence builder at this point. Make sure you can do it.